Okay, good morning everyone. This is it's 9 o'clock now, so I want to check your attendance. So in the first page of the attendance list, I can find 이재혁 씨, 고하늘 씨, 심준호 씨, 이승빈 씨, 이정태 씨. If you are here, then please leave your message. 네, 이승빈 씨 안녕하세요. 심준호 씨 안녕하세요. 이재혁 씨 안녕하세요. 이정태 씨 안녕하세요. 고하늘 씨 안녕하세요. Okay, we have all 5 students in the first page. Then next go to the second page. 이충하 씨, 정상아 씨, 홍주표 씨. 네, 이충하 씨 안녕하세요. 홍주표 씨 안녕하세요. 정상아 씨는 아직 안 오신 거죠? Okay, let's go to the third page. Then 김민선 씨, 김유신 씨, 배민열 씨, 배서령 씨, 서하연 씨. 네, 김유진 씨 안녕하세요. 김민선 씨 안녕하세요. 배민열 씨 안녕하세요. 배서령 씨 안녕하세요. 서하연 씨 안녕하세요. Okay, so now we move to the last page. Then I can find the name of 조대현 씨, 최승규 씨, 김성수 씨, Mr. 나단 마니큐어. 조대현 씨 안녕하세요. Good morning. 김성수 씨 안녕하세요. 최승규 씨 안녕하세요. Okay, great. I think that there is one missing student now. 정상아 씨 계십니까? Okay, then if you come, then please let me know. Then I will just check your late attendance. Okay. Then, okay, it's done. And good morning, everyone. I think that this is maybe, hopefully, this is the last lecture we have in online. So from next session, so lecture 10 on next Monday, we will meet together in building. So we have a building called C2. So usually previously it was called as ECS building B, but anyway nowadays it is called as C2 building, and we have a room, the largest room, like 203. So we will meet there, and as much as I know, so there will be certain thermometer to check your body temperature, and also yes, there will be some cleaning gel for our hand cleaning, and yes, what else? So I am a little bit afraid because that will be the first time to make the offline lecture. So maybe there will be some difficulties. However, I think that this is a really big step to our normal life. So please prepare some difficulties in on next Monday. Okay. So if I have additional information about our offline lecture on next Monday, then I will share it with you by announcing in our GES system. But anyway, if I do not send you any further information, then let's meet together. Let's see you on next Monday in building room C2203. Okay. So if you have any question about our offline lecture, in-person lecture, then please let me know. And also you can send me anytime your feedback or your comment on that matter. And also I am actually responsible about learning our lecture in safe fashion. So if you feel that something is concerned, then please let me know. So I will try to fix it, or at least make some decisions to avoid further difficulties. Okay, so then and it's time to receive your feedback about our previous lecture or homework. So if you have any question, then please ask me now. Then if not, then I will move to our ordinary lecture, lecture 9. And thank you, Mr. Sangsu Kim, because he pointed out the typo in our lecture 8, and it was my silly mistake. So the n is some number, however the physical unit should be like this. this is the typical unit we have to have for diffusivity. However, I made a mistake like this, so this is obviously wrong, so please use this number or this physical unit to have your answer. Okay, already the due is over, but I hope that every student has received my email for correction, so I hope that there is no problem. Well, is there anybody who can have a question? Then if you have a question, then please let me know. And once again, I wanted to remind you that many of you are actually communicating with me through the email. So, and oh, okay, Mr. Jeogli, thank you for your feedback. Okay, of course I can. So I will try to show the answer of a second problem. So why don't you go to our second problem? Okay. Okay. So you know that my homework problems are not copied from anywhere, but I just make it. So sometimes I can make some mistakes. So please, uh, please point out my mistakes when I make them. Okay, then I think that we can first of all magnify it. Yeah. Oh. Okay, can you see it more clearly? Okay, so okay, Mr. Zhang, so I will check your late attendance. Good. Then we are now talking about the second problem. So actually this is the second problem is directly related with our today's lecture 9. So what is the motivation of this silly question? So problem 2, it just shows that if we just consider certain diffusion component here, so don't care about the sign. So for y, just concentrate on its magnitude, and when you calculate q times dn times and dn over dx, then actually this q times dn is just a constant, and the magnitude of j is solely determined by dn over dx. So let's go to this part. Then let's say that here we have n-type region, and here we have p-type region. Then say that there is a certain point where two types are meeting together. So here up to here, that is really n-type, and here we have p-type. Then I told you that also we assume that the doping density, so donor density, is assumed to be 10 to the 20 per cubic centimeter. So this is just an example number, and Na accept density in the p-type region was assumed to be 10 to the 17 per cubic centimeter. Since this is really n dominant one, so electron dominant system, so we will think about the electron current density. And since here in this part, this means that this n-type region, so electron, the number of electron or density of electron is much larger than the number or density of holes. So we have electrons and holes, and which one is majority and which one is minority? So here majority minority is determined by its number or density, then certainly we can find that here in this n-type region, electron is a majority carrier type. So in this case, we can say that electron density would be almost the same to donor density, so 10 to the 20 per cubic centimeter. And how about this part? This means that now the p-type region. In this case, we can say that the number of or density of a hole will be close to the accepted density 10 to the 17 per cubic centimeter. So instead of that, since we have such a relation, so like the product between electron density and hole density is equal to Ni square. So we can find that electron density will be just 10 to the 3 per cubic centimeter, because at 300 Kelvin the intrinsic carrier density is more or less 10 to the 10 per cubic centimeter. So now you know it. So actually it's not that difficult. Also that was already pointed out in our previous lecture. Now you know that in n-type region you have 10 to the 20 and p-type region and 10 to the 3. But point is, when you try to calculate dn over dx, in order to calculate dn over dx, it is not solely determined by 10 to the 20, but not solely determined by 10 to the 3. So it is due to the linearly varying electron density approximation. So we will just have 10 to the 20 minus 10 to the 3 and divided by certain distance. So we will have a certain, how can I say, intermediate position where the electron density is linearly decreasing from 10 to the 20 to 10 to the 3. So why don't you just write down or draw something like this? So say that if this is better. Yes, let's say that this is x-axis, the position axis, and yes, this is the density. So density means that here electron density, so it has something like this. Of course, x will be have a certain length scale, for example micrometer. Then when we just write down, then we can certainly find that in this n-type region or p-type region, far away from this junction point, then it is certain that we will have a lot of electrons corresponding to what? Corresponding to 10 to the 20 per cubic centimeter. And also it is certain that if we go too far away from this junction region, then in this p-type region the electron density would be quite small, like just 10 to the 3. And by assuming this linearly varying electron density, then we can introduce some artifact number like this. Okay, for example here and there we can introduce, for example, delta x, where electron density is rapidly decreasing. Then how about this? If this is, for example, if this is the transition layer where electron density is linearly decreasing, then maybe we can think about certain graphs like this. Okay. And maybe we can draw something like this. That was my intention to give you the homework problem number 2. So in this case, so in this problem, I gave you 3 different numbers like and 1 nanometer, 10 nanometer, or 100 nanometer, or whatever. So when you have a certain number, then your answer will be just q times dn times, you know, this number, and you have to consider dn over dx. However, in this case, just to use dx or delta x, and please concentrate on this upper part, denominator. And when you have a look at this one, 10 to the 20 minus 10 to the 3, what does it mean? Actually, that is just 10 to the 20. So no contribution from this second term, minus 10 to the 3. So we will have just simply this form to calculate your answer. So the remaining task is just to insert your delta x value, then you will have the solution for then you will have a certain ampere per square centimeter. Okay, so Mr. Jayabli, so is it enough for your questions? I have tried to answer your question. Then could you please give me a further comments or further question? And also other students, you are really welcome to give me additional question or additional comment. Okay, so I'm just waiting your responses. So if you have further question, then please let me know. Okay, good, great. And you know that, so thank you for asking me this question. And yes, so you are always encouraged to give me a question, because we are not hurry in our lecture progress. Yes, because lots of my previous lecture are recorded and available, so I'm not in hurry to make a lecture progress, so we can move with our own pace. So please try to maximize your understanding on this subject instead of just skipping this one, skipping that one. Okay. Okay. So Mr. Chungari, okay. So yes, so actually, my intention to give you the problem number 2 was to initiate your curiosity like this. So you're quite right. So if you feel if you solve this problem, then certainly you can answer like this. Okay, here we have a certain j, and the value of j is certain number. I see. Also here, since dn over dx is exactly equal to that number, so we will have same j, and here we have same j. Good. But you know that this n plus p junction is an entire system. So for this entire system, we have one strong rule to be obeyed. What is it? It is simply the current flowing through this structure or this circuit element should be a constant. Why do we have such kind of thing? Let's think about once again. Let me just draw the schematic of this structure. If you remember correctly, then now we have here n plus region, and now we have here p region, and we are now looking at only this part. Yes, so we are now looking at this part because this part is the most important part in our discussion. So our x-axis can be actually regarded as the line running in this way. But anyway, my point is, where do we have the metal contacts or terminals which can be used to connect our circuit element to other circuit element? If you remember, then there will be certain metal line, and also in order to make a good connection, here we will have a P plus, and on top of this P plus, then we will have this one. Okay, however, from the electrical property, this right hand metal, this guy or that guy or this guy does not play at all because they are so highly conductive. The only important part now is this one, and this one is drawn here. So anyway, you know that there is a terminal number 1 and terminal number 2. Since there are only 2 terminals, then it is certain that the sum of first terminal current and second terminal current should be identically 0. So maybe you remember it. So this rule was maybe one of the first one we have learned in this semester. So you know it. Simply speaking, the current flowing through or entering into the device through the T1 and the current escaping from the device through T2 should be the same. So yes, so I fully agree with Mr. Chungari. So you are quite right. Yes, you are quite right. And this description is certainly long. Why do we have a long description? So here we have J in this transition region, so arbitrarily determined by myself. So we say that within delta X, electron density suddenly drop from 10 to the 20 to 10 to the 3 per cubic centimeter. However, if we try to calculate once again current density and once again current density in this part, what will happen? Yes, it is 0 because dN over dx is 0. And how about this? Yes, we have 0. Certainly, as Mr. Chungari correctly pointed out, it certainly means that this type of electron density, or just considering, how can I say, just considering the diffusion component in this system does not give us even current conservation in our circuit element. Okay, so current element, current conservation is a really important rule, so which cannot be disobeyed by this system. So simply speaking, this description or this kind of thinking is wrong. So that was my major motivation to give you problem number 2. Okay, thank you, Mr. Chungali, for asking me that interesting question. And how about other students? You guys also feel something strange? Why he is professor is teaching us or giving us a problem which does not make any sense? But that the reason is just to stimulate your curiosity about this system. So because this system typically called as PN junction, that is the first non-linear system you will learn in this microelectronics course, and that is actually the basic building component in our entire semiconductor industry. So understanding the behavior of this system is typically important. So I'm just giving you such kind of a nonsense problem. Okay, so students, so we are really on track. So we are not going to anywhere, and this is really related with our main discussion. So if you have further question on this kind of discussion, then please let me know. That is really important for your lecture progress. Okay. So please interrupt me anytime, even when I make a certain explanation. You can leave your message, then I will try to answer your question whenever time allows. Okay, so now you feel that oh, first of all, thing we have to understand is like this. Actually, we have a little idea about what is happening to this part. For this part, we have a little idea about the behavior of our electron density or something. But point is, at least we should be regarding it as granted to have electron density equal to 10 to the 20 at least the region far away from this junction point. And it is also certain that if we move our point of interest from the junction point to the left side, right side, then it is really certain that we will have electron density close to 10 to the 3 per cubic centimeter. Only interesting thing will happen just nearby the junction point. That is the thing we have to understand. So I'm now saying that although yes, this electron density profile looks a little strange, but it is certain that yes, up to somewhere here, electron density is really 10 to the 20. And here, up to certain point, our electron density is also 10 to the 3. So that is one thing. Then now we will focus on only the position or a region nearby the junction point. That will be my precaution or preliminary comment on this problem. Okay, so please give your question anytime you have any question. And then point is, now you feel that something is wrong, and say that now we have not applied any voltage difference between this part and that part. Okay, usually we will have a certain contact here and metal contact, and here we will have also certain metal contact. Then let's assume a certain case like we have applied just 0 volt to this left contact, and also we have applied 0 volt to the right contact, and it can be regarded as this form. We have a certain non-linear circuit element, and it has 2 terminals, and happen to be we just connect 0 volt to terminal number 1 and 0 volt to terminal number 2. Oh, yes, so voltage difference between these two terminals is actually 0. Oh, 0 volt difference is applied to this case. Then I wanted to ask you some question. Okay, then what will be the current? Do you have any idea? So we have a certain thing, certain circuit element, and we just apply 0 volt difference between two terminals, and of course it is there is no, how can I say, photon injection, or there is no temperature gradient, and we are just living in our usual environment and just applying potential difference, 0 potential difference, or the potential is kept as the same between terminal 1 and terminal 2. Then what will be the current? I think that you can answer quite quickly. So could you please leave your answer in the chatting log? So we have a certain circuit element, and the applied bias voltage or applied voltage difference is, yes, 0. Then if V equal to 0, then maybe you can expect that the current is also equal to 0. Then if you accept this concept, then this situation really strange. What is it? So we have applied 0 volt difference between left contact and right contact, and also it is certain that we have electron density, flat electron density at least somewhere, and flat electron density somewhere. Maybe you don't like my assumption like linearly varying electron density. Yes, I agree. Then I will give you some freedom to draw your own electron density over this transition rate. For example, you can draw it like this, or you can draw it this way. Any drawing is allowed. Then think about what will happen to your current density. Even in this case, whatever you draw, your current density in this part will be 0, and your current density in this part will be 0. However, even though you have a freedom to draw or connect these 2 points by your own choice, but your current density generated from our rule like Q dN dx cannot be 0. It is certain because at two boundaries, the left boundary and right boundary, certainly we have difference. One part we have 10 to the 20, and one part we have 10 to the 3. Then if we just make a drawing to connect these 2 points, anyhow we have to introduce a certain dn over dx, non-zero dn over dx, and this non-zero dn over dx is directly affecting our current density, which is not vanishing at all somewhere. Okay, so I hope that all of you understand this contradiction. So once again, here we have a PN junction, and we assume that we have applied the 0 voltage difference to these two terminals, and we expect that no current is flowing inside this system. However, when you have a look at this electron density, we feel that it is almost impossible to have vanishing electron density nearby this junction position. Okay, so is it okay for this reason? Okay, no gradient of electron density. Also this part, no gradient of electron density. But point is, here it is certain that we have significant gradient of electron density, and due to the diffusion mechanism, we have to have a huge amount of current density vector inside this part. So it is not allowed actually. So it is really contradiction to our assumption, like applying 0 voltage and therefore getting the 0 current. So I think that most students now feel that what happens in this course? So there is a certain rule, 0 current, which should be satisfied even for this system. But professor is giving us such a nonsense again and again. So how can we remedy this contradiction? So actually that's my intention, and I wanted to give you some time to think about how can we make our current 0 even in this transitionalism where electron density is really fastly decreasing to 0. So by the way, if you have any question, or if you cannot understand my explanation up to now, then please let me know. So I will be quite happy to answer your question. So then now remaining task is like this. Here, even in this part, we must have current density equal to 0. However, since the current density has the form of this, which is just proportional to what? To density gradient. So dn over dx. So it is not possible to have 0 quantity in this part. We must have a non-zero quantity. So now I wanted to tell you my main message. The vanishing current in this system at equilibrium case. Equilibrium means that the 0 voltage difference applied. In this case, it is certain that we have to have 0 current density everywhere. Not only this part, but every arbitrary position, we must have vanishing current density. Then it is an obvious contradiction from our assumption. What's wrong? The wrong assumption is this one. Up to now, we have thought that this one, the current density, the electron current density is dominated, was almost solely determined by the diffusion mechanism. So, you know it. It is because I gave you the form of current density, which is made of just diffusion term. So that's the reason why you have calculate only diffusion component. However, one thing I wanted to stress is this is not the case for our system. So there are two different mechanisms, dominant mechanisms in our semiconductor for determining the current conduction. One is obviously diffusion of our charge carriers. For example, if there is a position where many electrons are found, and if there is a position where almost no electron is found, then there will be strong flux from here, densely populated part, to less densely populated part. So there will be flux, net flux of electrons, and that will be translated to the charge transport. But there is one another mechanism we have not discussed up to now. The thing we have not discussed up to now is so-called drift. So simply speaking, electrons, our electrons and holes, they are charged particles. So for example, one electron has one negative elementary charge, and holes, although that is not a real particle, that is a quasi-particle, but anyway we will treat it as just carry one positive charge. So let me just write down in this way. In my lecture I will always use Q, which is positive 1.6 times 10 to the minus 19 coulomb. So one electron carry this amount of charge, and hole carry positive Q. This amount of charge is carried by one hole. So simply speaking, electrons are charged and holes are charged. So since they are charged particles, if we have electric field, then we can just push our electrons and holes according to their polarity. For example, let's say you know that we have tons of electrons here. Okay, then let's say that our electric field is the direction. Oh, sorry. I need to stress our vector. If we have electric field heading this way, so what will happen? So you know that the electric field, the direction of electric field is just aligned to the movement of positively charged particle. So if we have electric field heading to right side, then it means that our electrons, the motion of electrons will be dictated to, yes, movement of our electrons are dictated to the right side. So simply speaking, what I want to say is our basic assumption is we have to have zero current even in this center transition point, and just considering diffusion component cannot solve this contradiction. non-zero diffusion current. In order to make our current density really vanishes even in this central position, then we have to introduce the electric field, and the direction of the electric field should be this right side. So just our electric field push back our electrons. So are you with me? So let me just summarize this one. Let's assume that we have electric field at, for example, we have electric field in this way. Then now there will be certain competition of transport mechanisms. So one is, oh, we have a lot of electrons and we have no electron at all. So yes, let's move. So this will be the movement according to diffusion. And another one is, okay, in this part we have strong electric field heading this direction, right side. So the force exerted on our electrons will be just this direction. That will be the direction exerted on our electrons. So simply speaking, in this intermediate position or transition layer, we have a competition between diffusion flux and drift flux, and amazingly enough, they are exactly matched. So diffusion and drift, their contribution has the same magnitude and of course have different or the opposite direction. So that's the reason why, or that's the way we can have exactly vanishing current density all over our structure. So that was my message today. So I really wanted to ask you, all of our students, about whether you have understood my explanation up to now. If you don't understand it, then that is you are now missing the entire lecture today. So could you please repeat that you have understood my explanation? So simply speaking, sum of drift current and diffusion current component will vanish in this central part. Okay, if you understood everything, then please let me know. And of course, if you have a further question, it is even better. So if you can give me another question, then I will be even happier. Okay, good. And could you please, everybody, could you please leave your feedback? So I'm curious whether you have understood this important factor. Oh, Mr. Yushin Kim, thank you. Really thank you for your question. And although, let me just quickly answer to your question. Your question is, how about this part? So up to now, we have not thought about these positions which is far away from the junction region. In this case, oh yes, you are right. We have electron density which is constant as a function of position. But now you are now saying that how about the drift component in this part. If we have zero gradient of electron density, and if we have non-zero electric field, then obviously it is corresponding to zero diffusion, and this one is corresponding to non-zero drift. So we will have really non-zero total current density. Then, thank you, Mr. Yushin Kim, once again. As you correctly point out, this does not obey our assumption like vanishing electron current density. So that is wrong. We should not allow this one. Then what happens? Simply speaking, in this part, we have to have zero electric field too. Then, yes, then we will have a zero drift component. And same for this part. In this case, we will have a zero electron density gradient and no electric field at all. So then we will have zero electron current density even in this minority p-type region. So from the answer of Mr. Yushin Kim's question, it becomes obvious that, thank you again, it becomes obvious that in order to satisfy the globally vanishing electron current density, so we can have an important lesson that our electric field should be localized and concentrated on only nearby this junction. Okay, so here we should have zero electric field, and here we have no electric field at all, and only nearby the junction position we have a strong electric field which can cancel out the strong diffusion current. So that is my answer. So now you can understand that that situation. So for this, usually this part is called as neutral. So neutral, and this part is called also neutral because in this part the number of electron and number of donors which are positively charged are the same. So electrically this part becomes neutral. So this part is called as a neutral region. And also even in this part we have hole density, and which is equal to acceptor density, and accept ion itself is negatively charged and holes are positively charged. So since the number or density are the same, so also in this part we have a neutral. So simply speaking, in neutral region we have no density gradient, also we have no electric field. So in this part everything is just calm, quite peaceful, nothing happens. But in center part, actually, although we have no current density when we just have a look at it, however internally there are really two different current conduction mechanisms competing to dominate the current conduction. So that was a really good question. So simply speaking, the electric field should be localized around the junction position. That was my answer. And okay, let's go to the question of Mr. Ju Hong. And electric field is the external electric field. So what is the external electric field? So that will be a long discussion. But if we consider just the external electric field as the electric field generated by the voltage difference, then the answer is no. So please remember that the situation we are assuming now is here we have a terminal and that is grounded, and here we have a terminal and that is also grounded. So since there is no voltage difference applied between these two terminals, so no further electric field generated by this voltage difference. So even when the voltage of two terminals are the same, but we are now saying that in order to satisfy the zero current condition, our structure called PN junction should have internal electric field. So simply speaking, my answer to your Mr. Hong's question is thank you for your nice question, and that electric field is not generated by the voltage difference between your two terminals. It is internally generated due to the PN junction itself, or difference of doping density or doping polarity inside the system. Okay, Mr. Hong, is it enough for your question? So your question is really well aligned with our further discussion. So that is, I will explain it further. And okay, I'm quite happy to receive your questions, and amazingly enough, all of them are quite reasonable and quite interesting and well aligned to our lecture progress. But anyway, even not only this such a good questions, but even silly questions are welcome, because we have to learn. None of us are born as an expert in this field, so we have to learn. So you can give me any question. Okay, then if you don't have a further question, then let me just summarize the main message of today's lecture. Wow, so we are now talking about the PN junction where no voltage difference is applied to our system, and since no voltage difference is applied, we have to have zero current. That is our assumption. However, solely with the diffusion current density, we cannot support zero electric field inside our system, or zero current density inside our system. We have to introduce the diffusion term. We have to introduce the drift term to cancel out or compensate our diffusion term. So the direction of our electric field should toward the p-type region. So from n-type to p-type region. So in this case, we will have just to push back our electrons to n-type region. So if you have a further question about the lecture contents, please let me know. And now I will think about this one. It sounds great that we have a zero electric field, but zero current due to this internal electric field. Wow! But have you thought about the possibility to have the electric field? Oh, how can you have electric field? It's not like this. Oh, please give me the electric field. Okay, I will give you the electric field. No, electric field is solely generated by the charge, net charge. Once you have net charge somewhere, then there will be electric field. Electric field generated from net charge. So it means that if we wanted to say there will be the electric field, then certainly we have to say that there should be something. There should be something, or there should be some charges to generate the electric field. So think about a certain leaves in a tree, yes. So the leaves are turning around, then we can feel that, oh, in order to do that, to have such a behavior, there should be wind. Something like this. So if we really wanted to have the electric field, then what we have to have is charge. If we don't have charge at all, then nothing will happen. Although we are eagerly wanted to have the electric field, it is not possible. The only way we have the electric field in this electrostatic case, that is really the charge inside our system. So also we have a further constraint. Since the direction of electric field is in this way, this is the direction of our electric field, so we have to have positive charge here, and we have negative charge here. If we just swap this polarity, then what will happen? Minus, plus, then it becomes obvious that we will have the electric field like this. It's not possible to have such kind of a configuration. So now it becomes clear that in order to have the electric field, we must introduce the existence of positively charged layer in n-type region, and we have to assume that negatively charged layer in the p-type region. So otherwise, if we just swap that charge polarity, then everything just crash. No solution at all. So we must introduce this kind of polarity for our net charge density. Then natural question is, since this position is really n-type, the available charge carrier is only electrons. We cannot find almost no hole in it. And for this p-type region, we can find many holes. However, we cannot find electrons. But the real thing we wanted to have is, so electrons are negatively charged, but we wanted to have a positively charged layer. Holes are positively charged, however we wanted to have negatively charged layer. So, how can we have such a thing? If we add more and more electrons nearby this position, for example, let's write down the electron density, for example. If we add more and more electrons in this part, that cannot generate the negatively, that cannot generate a positively charged layer we wanted to have in this way. Now it becomes clear that in order to have positively charged layer at this position, the graphs of our electron density should run in this way. So are you with me? I mean that in order to have a positively charged layer, one possibility is adding more positively charged carrier. However, we have no positively charged carrier inside the n-type region, so forget about it. Another way to have a positively charged layer is just to eliminate the negatively charged carrier, so we can assume some behavior like this. So let's assume a certain behavior or graphs of electron density. Then what will happen? Let's try to the polarity of our net charge density. As I told you before, up to here, okay, it is neutral. Good, because number of electron or density of electron is identical to the density of positively charged donors. Okay, up to here, up to here, up to here, still we can have neutral region. However, when we move into this part, we found that although the donor density is still high, 10 to the 20, for example, however, we don't have enough electron, negatively charged electron, to compensate the donors. So now, if we believe this yellow curve represents the electron density, then we can find that here we have a layer of positively charged. Okay, so now we can have the way to provide a positive layer in this n-type region. Then how about the negatively charged layer in p-type region? From our discussion, it becomes really obvious that, okay, then now previously we assumed that there are so many holes and holes. However, if a hole is just eliminated from this part, then what will happen? Then we can say that, using the different color, if a hole density is this, corresponding to just 10 to the 17 per cubic centimeter, then everything will be just neutral. So everywhere we will have the neutral region. However, this is not we wanted to have. If we assume such kind of a hole distribution, not electron distribution, in this part electron is not that important, because this is in this p-type region, electron is just a minor carrier type. So if we have such a kind of reduction or decrease in hole density nearby the junction position, then here we will have just negatively charged layer. Oh, I'm asking you once again, how many holes? Oh, hole is almost nothing. There is almost no hole. And how about accept density? Atom cores do not move at all, so they just still there. So since they are negatively charged, then we can have negatively charged layer. So everything is quite consistent, and we cannot find any contradiction. So I think that today's lecture was devoted to the behavior of our p-n junction when we apply zero voltage difference. So usually that case is called as equilibrium case. So simply speaking, today's lesson was about the p-n junction at equilibrium. That was the point, and we have studied many things. And when we summarize our lecture today, then from the viewpoint, from the argument of vanishing current, we can find that in this junction there will occur certain intermediate layer where no hole, no electron, no hole, also no hole. Since this is a p-type, it is quite obvious, and no electron. Since this is a p-type, that is quite obvious. So we can expect that the existence of a certain layer where no mobile charge carrier is available. We can understand, or we can expect the existence of a certain layer where we cannot find any mobile charge carrier. Although we have doped these regions with n-type region and p-type regions, so our naive expectation is everywhere either we can have full of electrons or full of holes. However, when we make a junction between these two regions, then it gives us certain intermediate layer where no available charge carrier found. So this part is very significant for p-n junction. Okay, the time is up, and I think that we have a short time to receive your really quick question. And if I think that this part is kinds of most important part in the p-n junction study. Of course, in the next Monday, we will expand our discussion to the case where voltage difference is applied to our p-n junction. But important thing is first understanding this equilibrium state is really important. Based upon this understanding on the non-equilibrium case, then we can expand it to non-equilibrium case. So if you have any question, then please send me an email. I will be happy to answer your questions. Okay, thank you for your participation, and yes, next Monday, see you in building C2, room 203 at 9 o'clock. Okay, thank you. Bye.